Hello everyone, welcome to the NPTEL course on computational process design. Once several alternate flowsheets are obtained, these alternate flowsheets are assessed using different criteria. The first criteria to assess the alternate flowsheet is economic evaluation. In this, once the mass and energy balance is established, the cost of equipment and the cost associated with purchasing utilities are analyzed to calculate the cash flow to the company. This cash flow is then compared with the cash flow obtained in other competing projects to evaluate the worth of the proposed project. In addition to the economic evaluation, there are several other evaluations are also there, like whether the given flow sheet is satisfying the environmental regulation or not. In this, emphasis is given on complying with various government regulations related to air, water and land pollution. Also, safety analysis is important, which highlights the necessity of conducting hazard studies to identify and mitigate process hazards. Whether the obtained flow sheet is flexible enough to accommodate different changes or not, this has to be checked. So process flexibility describes the need for processes to adapt the variations in inputs and operating conditions. Common example is a petroleum refinery where different types of crudes are processed. And the last important criteria to assess the process flow sheet is the controllability. So it addresses the challenges of maintaining the process stability during the dynamic changes and disturbances. So the important question here is how we can generate and search different alternatives. So the best alternatives has to be found out from several possible alternatives generated, and there should be a systematic way of generating these alternative flow sheets. The simplest way to generate the alternative flow sheets is a exhaustive enumeration of the entire search space, where every alternative is generated. This option is feasible when the number of enumerations is small. A common example is shown here, where there are three hot streams are there exchanging heat with the three cold streams. You can see that if we take an example of cold stream 1, which can exchange heat with hot stream 3, hot stream 2 and hot stream 1. So there are different possibilities are there. It can have the exchange with any one of these or with all. Also, the flow of these streams can be co-current and counter current. So all such enumerations one can check in the exhaustive enumeration, and based on that finally the best flow sheet can be selected. So clearly this particular methodology is extremely time consuming and can be performed only if the number of enumerations are small. But if the number of enumerations are large, in such cases a more coordinated search involving the tree search in the space of the design decision is performed. So in this particular case, each node point on the tree, we record the assessment and the decisions prior to the branching further. At each node, the method assesses the current design and decides whether the continue branching or prune the search space based on the partial evaluation or not. So in this case, you can see that whether the flow sheet is completed at this node or not. If it is not, in that case the branching is continued. The method also allows backtracking to previous nodes to explore alternate decisions, optimizing the search process. This particular methodology clearly is a extension of branch and bound algorithm, and this commonly referred as a decision tree in a machine learning jargon. So you can see that one such example is shown here in the context of the same case study which we have studied. So remember that from the reactor, different components coming out are methane, ethylene, propylene, diethyl ether, ethyl alcohol, isopropyl alcohol, water and crotonaldehyde. We can separate these components by using different methods. So if we select the distillation, in the distillation we may select separating methane from ethylene, or we can have a option of separating ethylene and propylene. So based on that, we will get a different nodes. Similarly, if we are using another separation methods like flash and absorption, in the flash and absorption, the separation is happening between non-condensable and the condensable gases. So here you can see that the non-condensable gases and the condensable gases are separated, and they are further refined in the subsequent separation units. So in this manner, we can represent the entire separation process in terms of different nodes and trees. The another method of generating the different alternatives is evolutionary method. So in evolutionary method, we start with a base case design, and this base case design then we improve in an incremental manner. So in this we do the improvement which can be made and incorporated in a predetermined and programmed way. Since the incremental improvements are performed, sometimes this can be automated. The next important point is postulating the superstructure of the decision. So often we see that the entire superstructure of the decision can be formulated. A example can be, if you look at the heat exchanger network here, how many possible cases are there for exchanging heat between C1 and other streams that we can enumerate here. So you can see that C1 can exchange it with H3, H2, H1 in a co-current and counter current manner. So clearly the entire superstructure can be formulated, and once this superstructure is formulated, then the best decision can be obtained. So next important point is establishing the target for the design, like minimum utility requirements. This type of targets very often helps in rejecting the designs that exceed these targets and guides the generation of the network that meets this target. So a common example could be, so if the amount of utility is higher than the minimum value specified, in such cases these designs are eliminated. The next important point is very often the problem abstraction is used. So problem abstraction is nothing but what? Problem abstraction is nothing but representing the flow sheet in a simple way like this. So here you can see that the common equipments are grouped together. So for instance, here this feed preparation equipments are grouped in this in one block, and all the separation units are grouped in the recovery block. So this type of representation is called as a problem abstraction. So when we have a problem abstraction, it helps in generating a range of design alternatives by formulating a less detailed problem statement. It groups part of the problem that behave similarly. It reduces the size of the subspace. Again, the decision made in the abstract space affect whole families of the alternative, making the search for better design more efficient. So what we can say here that the decisions made are actually applicable to the entire block, entire group of the equipment. For instance, here you can see that whatever the decision we are making up after the reaction, that will be applicable for this entire recovery block. So this recovery block may be having different equipments here as shown here, but the decision will be made for the entire group. Now what we wanted to see is a decomposition strategy for process synthesis. So clearly large number of alternatives are possible, and clearly we will not be able to evaluate each and every alternative. So in order to ease out this problem, typically a partial order or a decomposition of the decisions are performed while developing the flow sheets. Commonly used decomposition strategy is to break the given problem into smaller manageable parts. uh, Typically three important steps are performed in the decomposition strategy. So for a process flowsheet development, by considering the reaction first, the subsequent design choices are reduced significantly as it limits the effective use of available raw materials, and it dictates the need for material recycling and product recovery. So by taking the reaction first, several alternatives can be eliminated. The next step is, once the reactions are selected, the next step is to connect various chemical sources such as raw materials and reactor effluent with targets like products, byproducts, waste streams and reactor feed, which define the separation task in the flow sheet. And the third step is, once this preliminary flow sheet is developed. The last step, we look at the energy network, considering the options like using reactor effluent cooling to prevent to preheat its feed, or employing a distillation columns condenser to preheat the feed of the another column for efficient operation. So what we are saying here is, so very often in the last step what we do is, uh, whatever the effluent coming from the reactor, if it is at a hot condition, this hot effluent can be used for preheating the feed. That can improve the energy efficiency. Another option which is used regularly is, when we are using the condenser in the distillation column, this condenser can be used for preheating the feed for the next distillation column. So both these options can increase the energy efficiency of the process. So these three steps are performed for decomposition of the process synthesis. Next is, when different flow sheets are generated, we use the bounding strategies to evaluate these different flow sheets. So the bounds should be used on evaluation criteria to eliminate unfavorable process alternatives. Early decisions in the hierarchy have a greater impact on the process economics. However, if you look at the subsequent decisions, typically have a lesser effect on the final outcome. Usually we take the profit as a example criteria for assessing the impact of the design decisions, but instead of profit we can use even the sustainability or uh, uh, environmental protection, or how much environmental degradation a particular process is performing. That can be another criteria to look at the assessment of the given flow sheet. The process space is partitioned based on decisions. Each partition is explored to find constraints and maximum profit bounds, guiding further search and the design completion. Designs that do not meet certain constraints or fall below the profit or of a completed design are eliminated. A common example is taken here. Let's say if you are having a reaction occurring in the process, and based on the pure stoichiometry, if you calculate the profit, and the profit comes out to be $100, but let us assume that this reaction is also having a side reaction where around 10% of the raw material is converted to a waste product. So if we account this side reaction, the actual profit which we can earn maximally comes out to be $80. So we can see that the initial search space we have reduced by using a another block which is present here, the white colored block. Again, in this particular block, clearly none of the designs can have, none of the flowsheet designs can have a higher value than the $80. So so within this design space, further the constraints are added. For instance, for the given process, let's say the products are separated by using distillation. So when the products are separated by using the distillation, that particular search space is represented by using this dotted line. So anything below this dotted line here represents the separation by using distillation. Again, in this particular block, uh, we can see that there are two blocks here. One is the yellow block on the left hand side, and there is a white block on the right hand side. So in the right hand side, again this given search space we have partitioned into two different blocks. The first block is this, and the second block is below that. In the second block we have completed the design, and let's say that the profit obtained in the second block comes out to be $60. Now the other block which is there on the left hand side, which is shown by yellow color here, which is having the profit of $70, but this design is not complete, whereas the design here in this particular block is complete. So again, in this left hand side block, we can look at the different constraints present in the problem in order to complete the design. And let's say we come across another constraint, and because of that constraint the profit actually reduces to $40. So clearly one can see that the block which is shown by a green color here is having a lower value of the profit compared to this completed design. So clearly this particular block has to be eliminated. So in this manner, eventually by addition of the constraint we are reducing the surface and eliminating the design options which are having the lower profit than the completed design, and also we are trying to find out different alternatives here. So with this we can find out the best design after looking at all the options. So in order to decompose the problem into lower parts, a hierarchy method is given by Douglas. So he has listed 5 steps. These 5 steps basically comprises of different operations. So level 1 is choose between batch and continuous process. So typically if you see, the batch processes are used for pharmaceutical, food and specialty plastics, where quick market entry or small production volumes are needed, whereas the continuous processes are generally more cost effective and are preferred in the other cases where large amount of uh, product has to be produced continuous manner and the demand is present over the years. In level 2, we examine the number of raw material and product streams, the presence of byproducts and inner components. So it also considers the necessity of process, recycle and purge. So depending on what type of raw material we are using, it gives the information that whether we will be requiring recycle or purge. Recycle and purges are required or not. For instance, if the feed is not pure, in that case we might be requiring a purge, or if the conversion is not high, in that case we might require the recycle of the raw material. So based on the reaction chemistry, these decisions has to be taken by analyzing the raw material and the product streams. Level 3 is to investigate the recycle structure of the flow sheet, focusing on the reactor network and their interactions through recycle streams. It also assesses the impact of reactor conditions on the overall process. Level 4 decision is the decisions are made regarding vapor and liquid recovery. This includes the selection and placement of the separation units, the sequencing of separators and their operating conditions. And in the last level, level 5, uh, it deals with the design of the heat recovery network after all the flow sheet decisions have been made. This involves optimizing the heat exchange between the different process streams to improve energy efficiency. So this entire methodology given by Douglas, we are going to evaluate on the same case study which we have studied so far. So let's look at this case study again. This is the same case study we have started. So in this particular case study, you can see that this flow sheet is primarily for the case when the ethylene is having the purity of 99.996%. But in the given problem statement, the ethylene feed has 96 mole percent ethylene, 3% propylene and 1% methane. So how to accommodate this actual flow sheet for this changed feed condition is what we are trying to understand. So now let's look at the bounding strategy in order to understand uh, whether this particular process is going to be beneficial for the company or not. So clearly the company was intended to sell 1,50,000 meter cube per year of the ethyl alcohol. So with respect to this demand, we are trying to understand whether the process is going to be profitable or not. So let us consider that the selling price of ethyl alcohol is $0.713 per kg, and assume that the price of the ethylene is $0.4 per kg. And also the ethanol obtained in this flow sheet, you can see that the ethanol product which is coming out from the last distillation column is actually a 85% ethanol and 15% water. That is the azeotropic mixture of ethanol and water. So in this case, we can calculate the molecular weight of the product coming out from the distillation column. So 85% is the ethanol. So we can multiply 0.85 to 46, which is nothing but the molecular weight of ethanol, plus 0.15 into 18, that is the molecular weight of water. That gives us 41.8, which is a molecular weight of the product stream coming out from this last distillation column. So again we can calculate the mass fraction. So mass fraction in this case comes out to be 0.85 multiplied by molecular weight of uh, ethanol divided by molecular weight of this entire stream, so which is nothing but 41.8, so that comes around 0.935. So, and from the literature, the density of the this product stream which is coming out, the density of this product stream is reported in the literature as 810 kilogram per meter cube. So using this particular information, we are converting 1,50,000 meter cube per year of the uh, ethanol which we wanted to sell in terms of kilomole per year. So for that we have multiplied 0.935, which is nothing but the mass fraction, into 1,50,000, that is meter cube per year, into the density of the product, which is 810 divided by 46. So that gives us uh, 2,469,619 kilomole per year. So this many kilomole per year of ethyl alcohol uh, is required. So again, if we assume that this ethyl alcohol is uh, this ethyl alcohol is uh, uh, obtained after 100% conversion of ethylene, so in that case we wanted to find out how much ethylene is required. So if we calculate the amount of ethylene required, so amount of ethylene required we can directly, so this many moles are required for the ethyl alcohol. So clearly 1 mole of ethyl alcohol is going will be produced by 1 mole of ethyl uh, uh, will be produced by 1 mole of ethylene. As you can see, the reaction is given. So reaction, if I go back and show the reaction, so see, 1 mole of ethylene is producing 1 mole of ethanol. So clearly the same number of uh, kilomoles of ethyl alcohol will be required for ethylene also, and we can convert in a mass unit by multiplying a molecular weight. So after multiplying the molecular weight, we get the amount of ethylene required, which is nothing but 6 crore 91 lakh 49,347 kg of ethylene per year. So once we have obtained this ethylene, remember this ethylene feed is having only 96% ethylene, and the remaining is 3% propylene and 1% methane. So we can calculate the amount of propylene required and the methane required, and that comes out to be 32 lakh 41,374 kilogram of propylene per year, and 4,11,603 kilogram of methane per year. And we can sum these three quantities, and that gives us the total amount of feed required over the year. So we will be requiring almost 7 crore 28 lakh 2,324 kg per year of the feed in order to satisfy the demand given by the sales department. So this particular amount is for the ethylene. We can multiply to the cost of the ethylene, which is 0.4 dollar per kg. So that gives us the cost of the raw material required. So in this case, this amount is multiplied by 0.4, so that gives around $29,120 per year. This much amount is required for as a cost for ethylene. And now we are calculating how much revenue we will be getting by selling the ethyl alcohol. So this is the 2 crore 46 lakh 9,619 kilomole per year of ethyl alcohol is there. We can multiply by 41.8, so that gives us the kg of ethyl alcohol multiplied by the cost, which is 0.713. So it comes around almost 73 million dollars per year will be the revenue by selling the ethyl alcohol. We can subtract the cost of this raw material, which is nothing but 29,120. So after subtracting, we get almost 73 million dollars as a profit. So clearly this profit has to cover up the annual operating cost as well as the levelized fixed cost. This profit calculation indicates that the process is economically viable, and we can further look at the sensitivity of all these numbers by varying the cost of the ethyl alcohol prices. So ethyl alcohol price here we have taken as 0.713, but let's say if we assume that 20% plus or minus variation in this, in that case what will be the profit, that we can easily calculate. And with respect to this variation also, we can see whether the process is economically viable or not. So in this case it seems like, since the profit comes around 73 million, this process is economically viable. So once this is done, then now we wanted to evaluate uh, the uh, the obtained flow sheet. So for that we are using this decomposition method suggested by Douglas. So in the level 1, clearly in the level 1 we have to select whether the process should be batch or continuous. So if we see that the ethyl alcohol, which is a commodity chemical which is regularly used, so clearly it is going to remain in the market for a longer period of time, and also its demand is spanned over the entire time in a continuous manner. Therefore producing the ethyl alcohol by using a continuous method is more appropriate compared to the batch production. Level 2 decision is, we have to examine the number of raw material and product streams, the presence of byproducts and inner components. So clearly you can see that the feed here comprises of 3% propylene and 1% methane. We can decide to separate these 3% propylene and 1% methane from the ethane, from the ethylene, but that is going to be costlier, primarily because it will require a heavy duty condenser. So that is not a viable option. So in such cases what we can do is, we can pass this propylene and methane directly to the reactor, and then we can separate the byproduct or these reactants in the separation steps. So based on this we have formulated different flow sheets which we have discussed earlier. I'll go back again. So these are the two options we have looked at, but there are multiple alternatives possible. So here you can see that we are looking at separating propylene and methane from the raw material, and then the pure ethylene is passed to the reactor. So clearly this particular alternative is not viable, but another alternative where ethylene, propylene and methane mixture is charged to the reactor, and then propylene and methane are separated. uh, also also the byproduct like isopropanol are separated in the subsequent recovery unit. So clearly different options we can check in the level 2, and based on that the best option we can select. In level 3 we investigate the recycle structure of the flow sheet, focusing on the reactor network and their interaction through recycle stream. So clearly in this particular case study there are two reactions occurring. First one is the desired reaction, where ethylene is reacting with water to produce ethanol, and in the second undesired reaction ethanol is reacting with itself to produce diethyl ether and water. So you can see that uh, the selectivity is a very important point here, primarily because if we let this undesired reaction to occur, in that case uh, some of the ethylene will be used for producing the diethyl ether. So the selectivity is going to be different, and based on the selectivity we have to again calculate the profit one more time, and we have to see whether the obtained profit with this selectivity is actually beneficial or not. Another option could be, in this case you can see that this undesired side product is produced. Now this second reaction is a equilibrium reaction. So if we recycle this diethyl ether again to the reactor, in that case what is going to happen is this second reaction is going to get suppressed, and the additional amount of ethylene will not get converted to diethyl ether. So we can make such decision where we have to see whether we can recycle back the undesired side product in order to suppress the undesired reaction and to improve the selectivity. So this type of options we can get directly in the level 3. So with this recycling of the diethyl ether, there will not be any selectivity loss uh, uh, in order to produce the ethanol. So level 4 decisions are regarding the vapor liquid recovery. So you can see that the feed comprises of methane and propylene. So the product coming out from the reactor will be comprising of the non-condensable gases. So these non-condensable gases will include methane, ethylene, propylene, and this has to be, and in addition to that we will be having some amount of uh, diethyl ether and ethyl alcohol. So these has to be separated. So these has to be separated in the scrubber. In the scrubber, only the condensable gases like diethyl ether and ethyl alcohol will be taken out with the water, whereas the non-condensable gases like ethylene, propylene and methane will come out from the absorber, and this has to be first splitted by using a splitter, and in the splitter, uh, we can have two fractions. So, and one fraction will be purged, whereas the other fraction will be recycled back to the reactor. So in this case you can see that the maximum amount of methane which can be built in the reactor is given as 10%. So clearly we have to select the purge fraction in such a way that the amount of methane build up in the reactor should be less than 10%. So based on that, this purge fraction has to be selected. Again, similar to this for the propylene also, the some amount of propylene will be purged and the remaining will be recycled back. Similar to the vapor recovery, the liquid recovery, if you look at, in the liquid recovery, the liquid which is coming out from the flash unit will be primarily water rich, and this water rich stream will be first sent to the distillation column, where predominantly the water is removed along with the crotonaldehyde in the first distillation column. Then the remaining components which are present in the distillate will primarily will have the volatile compound like diethyl ether. So we can separate a diethyl ether in the second column, and once the diethyl ether is separated, the separated diethyl ether will be recycled back to the reactor, and uh, the bottom product coming from the second distillation column then will be charged to the third distillation column, where the ethanol, 85% ethanol is separated from isopropyl alcohol and trace amount of water in the third column. So finally, once this flow sheet is finalized, in the last step what we have to do is we have to represent this entire flow sheet in terms of the heat exchanger network, and we have to see how we can utilize the heat uh, in an optimal manner. So the flow sheet is further refined by including additional constraint, if any. This involves optimizing the heat exchange between the different process streams to improve the energy efficiency. So with respect to this Douglas hierarchy, we can see that how the given problem can be modified. So remember that the previous figure which I have shown with respect to the case study 1, we did not had this recycling of the diethyl ether. You can see that we have now recycled the diethyl ether back to the mixture, where the water and the compressed ethylene, propylene and methane feed is mixed, and this mixed feed is then charged to the reactor. Again you can see that in the reactor, ethylene, diethyl ether and ethyl alcohol will be separated in the flash unit, and that in this case, in addition to ethylene, we will be having propylene and methane. So propylene and methane will be there in the gas. In the absorber, diethyl ether and ethyl alcohol will be scrubbed by using the water, which will be again mixed here, and the gas coming out from the absorber will be comprised of ethylene, propylene and methane. So this ethylene, propylene and methane then will be recycled back to the reactor. So we stop here and we will continue with the heat and mass balance in the next class. Thank you.